Okay, but why?
Hello there, and welcome to the second episode of Biscuits in Biophysics. Now, in our last episode, I introduced you to biophysics and mentioned that it can be divided into the analytical biophysical techniques, which don't involve imaging your molecules, and the structural biology techniques, where you do image them. Now, when it comes to imaging, regardless of the type of technique you use, the essential principle remains the same. I shine some waves of radiation onto a sample of molecules, and these waves get scattered by the molecules, after which they hit the detector to form the image. Now let's talk about the contrast that's generated in the image. Of course, as some of you might be thinking, it does depend on the number of light waves that meet at a particular point in the camera. The greater the number of waves, the brighter the spot. But that's not the only thing that generates contrast in an image. The thing is, when it comes to waves, it's not just about how many of them meet at a point, but also when they meet at that point. For instance, let's consider these two waves, which look identical in every way, right from their height, which defines their brightness or intensity, and their frequency as well. Now, when these waves meet at a point of the detector, you get a combined wave that's twice as tall, which means the brightness is twice as much. But what happens when one of these waves is ahead of the other by, say, about this much? Now, as you can see, the drop of the first wave aligns perfectly with the peak of the second one. So when they meet at the detector, they perfectly cancel each other out. And the resultant wave is actually not there at all. It's zero, which means you get a perfectly dark spot. This time delay between the waves, which we call phase difference, is also important in contributing to image contrast. In fact, phase is so important that if I take the intensities from the image of a cat and combine it with the phases from the image of a duck, then the image I get by combining them is the image of a duck. There's no trace of the cat anywhere, even though I took the intensity straight from it. So the phases actually dominate in the effect of the contrast in the image. So it's kind of strange that people don't really talk much about phases and don't seem to relate to, wait, of course. Ladies and gentlemen, this is I. I has a value of the square root of -1. So you would have heard of him with his other name, imaginary number. Now I know that the moment I said that, your brain said, oh, imaginary. That means I don't need to take this seriously at all. And that is the exact problem when it comes to teaching these concepts in school. You don't understand the point of it. It feels like it's not going to be useful to you in life at all. I see tons of people who tell me, we use real numbers to count time and money and distance and everything, but we don't use imaginary numbers that often in life at all. Where do we encounter it? Well, if you ever want to describe the shape of a snowflake, or you turn on an electrical appliance without getting electrocuted, or you flick an ant off the fourth floor of a building and it lands on the ground and still continues to walk like nothing ever happened to it, then remember that you cannot answer these questions without using imaginary numbers. So yeah, imaginary numbers are pretty much all around us. Yeah, they don't probably appear too early in your life like the other numbers that you've learned. But hey, you didn't learn about the square root of 2 or pi until you were 13 either. That doesn't make them any less real, does it? And if you're wondering, right, but where exactly do imaginary numbers fit on our number line? Then I have a question for you. Why do all the numbers need to fit in exactly one line? Think about it. And just like that, I can keep naming tons of applications in real life which wouldn't work at all without imaginary numbers, and I haven't even got to the biophysics yet. Now, as biophysicists, we would lose our jobs if it weren't for imaginary numbers. There are people who are hired to work on expensive equipment just to identify the imaginary phases of an image in structural biology. In fact, we are so desperate to find the phases of an image that we deliberately go out of focus when we use a microscope. Man, if I had any clout in this channel, I would use it to start a campaign called #Imaginary_Lives_Matter. Because trust me, we do need it. So now you finally understand how important and commonplace imaginary numbers are in our lives. In fact, as a structural biologist who regularly uses imaginary numbers to study tiny atoms and molecules, I would argue that imaginary numbers are absolutely crucial to understand our lives. Think you can come up with a counter for that? So the next time someone disrespects Mr. I or imaginary numbers in general, just remember to phase out of the conversation. See what I did there? And on that note, I imagine you've learned a lot this episode. I'm Varun from OK But Why. Stay safe, stay curious, and stay tuned for tomorrow's episode.